Alright, this is the video for Lab 12 for Math 215, and I really wanted to say that just congrats to everybody watching this video. I know it's been a really weird semester and a hard semester, but you've gotten it this far, and I think that's something to really be commended, so keep up the good work. So starting out on problem 1, just orthogonal check. You take two vectors, u and v, and you want to see if they're orthogonal or not. Now if you remember, orthogonal is like perpendicular except in 3 dimensions, and if you remember, two vectors, if their dot product is 0, that means they'll be orthogonal. Like if that was I and that was j, when you dot them together you'll get 0 because that's orthogonal. And so we can see if they're orthogonal, their dot product will be very, very small. Ideally 0, but because of some machine error they explain here. So what I would do is I would say np dot dot of u and v, and then I would make sure to do the absolute value of that value, because it could be like -1, but if you say if -1 is less than like 1 to the -12th, it will be. But you want 1 to be not less than 1 to the -12th. So this is saying if the dot product is 0 or very, very close to it, then you want to return true. They are orthogonal, otherwise return false. Moving on to problem 2, you want to use your data from problem 1. And the way that I would do it is we have a whole list. Let's say we have 4 vectors that we want to compare. So we want to compare 1 with 2, 1 with 3, and 1 with 4. But we also want to compare 2 with 3 and 2 with 4, and then we lastly want to compare 3 with 4. So we need to do all these different iterations. That kind of is confusing because we don't know how many we are dealing with. We're just dealing with n amount. And so the way that I would go about it is note how for 1 we compared it to 2, 3, and 4. So I'd say for I in range, let me make sure that I write this down correctly. Yeah, so if your vect set, I'm going to say n is the length of my vect set. Something like that. So I'm going to say for I in range n, so I'll look at every one, but then I'll want to make a second for loop. And this will do for j in range. And if we look at 1, we did 1, but then we compared it to 2 to start off. Or when we started with 2, we compared it to 3. So we always want to start at the first value after the one that we're dealing with currently. And then we want to go to the very end. So if I is 1, then j will start at 2 and go to 4. If I is 4, for instance, notice how we didn't compare 4 to anything. Then this will start at 5. But 5 is after 4, that n, and so that won't run, which is what we want. Whereas if that's 3, then that will start at 4. And so that's how you'll set up your for loops. And I would just run orth set check with your vect set at I and your vect set at j. And a nice way to kind of catch to see if anyone fails is, this should be indented, but I'd say if not orth set check, because you want to see if they're all orthogonal. And so the opposite of all of them being orthogonal is one of them not being orthogonal. So even if this just happens once, if you don't have orthogonal vectors only once, then you would return false. However, if every single one is orthogonal, this will never trigger, and so at the very end, I'd then put return true. So if one fails and catches the statement, it'll return false and quit. But if you go through and you never hit this statement, then it will return true at the very end. So that's how I'd phrase that one. Problem 3 and 4 are actually pretty easy. Problem 3 is just talking about, it wants you to find the unit vector in the direction of the vector that you're given. The really nice thing is that there's actually a function in the NumPy library for this, and it is np.normalize. Or sorry, no, that's the one that we're dealing with. It's np.linalg.norm. And this doesn't actually normalize it, but it gives you the length of the vector. So if our vector is like 3, 4, then the length or the magnitude of that vector will be 5, because it's 3 squared plus 4 squared. Square root of all of that. And so np.linalg.norm of your vector will return the magnitude. And to make a unit vector, you may remember, we will divide by the magnitude. So if this is our vector, we're going to divide by the magnitude to get our unit vector. And that's all we'll return, is just this u, or this equation itself. And then for problem 4, it wants you to find the projection. And they explain the projection formula right above problem 4. This projection of A onto B is A dot B over B dot B times B. And so yeah, keep in mind that these are both dot products. You'll do np dot dot A comma B, np dot dot B comma B. And so these are both scalar quantities. They're just numbers. And so this whole thing is going to be a number. And so you can save that as like x or something and just times it by b. These are not both vectors or matrices, so you can just times them normally. And make sure you phrase it like this when they say projection of A onto B. So that's problem 4. And then the latter half of this lab is actually probably the harder half, but I'll hopefully be able to step you guys through it for each problem. So Gram-Schmidt is saying we have a list of vectors, v1, v2, v3, v4. And we're returning the list of orthonormal vectors which span the same space. And to do this, we'll just replicate the pseudocode that they give us in the problem before. And so yeah, that x equals v will be your x equals v dot copy, n equals length of v. Just remember for your for loops, when they use this notation, this can be confusing at first if you're not really taught what it means. This in Python translates to for I in range, and then our starting point is always going to be this value, so 1. And our ending point is going to be 1 past this value because range never includes the last value. Because they want I to run with n minus 1, so we'll say n, so it goes to n minus 1. Remember that for the next one as well, for that I minus 1. And you don't need to include the do, that's just part of the pseudocode. And then your x sub I will be x at or bracket I with that notation. And your projection of v comma I and or vi and xj. Remember the way that we wrote out our projection was projection of AB is the same as this. So when we run that projection, we'll want to do projection of vi comma xj. Just make sure you don't swap those because it will run the code incorrectly. And then those bars in the next problem is just the magnitude of x of I. So you could just say, I guess I'm running out of room. For the next part, you could say x equals x at I, my bad. X at I equals, I think it's called normalize is the function that we created. Normalize x at I. So hopefully that helps with problem 5. Yeah, problem 5 is just a lot of copying pseudocode. So as long as you can get that down, it shouldn't be too difficult, hopefully. Now moving on to problem 6, which I would argue is the hardest problem. And I'll back up a little bit to explain it, hopefully. We're given a matrix A, and we want to get a matrix Q, and the relation between these is that Q has a bunch of columns that are orthonormal vectors. And those orthonormal vectors inhabit the same column space as A, meaning they're the orthonormal vectors based on the columns of A. So if we first want to get the columns of A, we'll use that list comprehension that they have in the textbook. I'm probably not going to write out all of it, but I think you see what I mean. Or that's not an I, that is a colon. This is in problem 5, or problem 6, the rest of this. And so that's how you'll get the columns of A. And you want to plug the columns of A, I would call it like something like that. You want to plug that into your, here I'm just going to write it out. Your columns of A will be that whole np.array function that they have in problem 5. And then you want to plug those columns of A into your Gram-Schmidt function to get your orthonormal columns of Q. So I would say columns of Q equals Gram-Schmidt of columns of A. However, we don't want the columns of Q, we want Q itself. And so this is what I would suggest. This is very, very similar to the columns of A. It's saying if we have a list of the columns, then to get the original Q matrix, we would do np.array. My bad, that should be a parenthesis. np.array columns of Q at, and that's a colon, by the way, and that's my I, for I in range of the length of A. Sorry for the two separate lines there. But that will get your Q based on your columns. And this is like, it's doing something similar to the transpose, but because of the whole like NP array versus list, this is the way that I would write it instead. And so once we have Q, we can figure out R just by doing the transpose of Q times A. And it is a matrix multiplication because these are both matrices. So I want to do A or the np.mapmul. Oh, sorry, you can't see that. There you go. So that finishes up problem 6. And you'll want to return Q and R for that one. Again, that's probably the hardest one. But moving on to problem 7, once you have that, yeah, I guess write that down really quick. Once you have that, you want to do the QR solver, which given A and B is going to give you your X. And so yeah, if we look at that line that they specify above, this Rx equals Q transpose times B, we know that we can run Q and R from our QR decomposition of A. And to get our, I would call this whole thing like capital B or something, and B would be what we get from doing the mapmul of the transpose. I'm not going to write that out, but I think you know what that means. That's just the transpose of Q and B. And then we do back substitution to get this X, where we say X is back substitution of, let me just make sure I notate this right. It would be of R and B. And they already give you the formula for back substitution, so that should help. And then you'll want to return X. And so yeah, that will be your QR solver, which is the last problem. So hopefully that'll make sense. Again, the last half of this lab is kind of tricky, especially conceptually. But again, kind of for the whole QR decomposition, you'll take the columns of A, turn them into the columns of Q, then flip Q back to get your regular Q matrix, and then you can go on from there. And so I hope this helps, and have a great week.